I'm Hiyori Itsushi from Keio University in Japan. I will be presenting a paper titled Smartphone-Based Teaching System for Neonate Soothing Motions. Soothing motion is action caregivers take to calm crying babies. However, inappropriate soothing motions can negatively impact the physical and socio-emotional health of infants. Therefore, it is important for caregivers to learn appropriate soothing motions. This is especially important for first-time caregivers because they might lack essential knowledge of neonatal nursing and lead to incorrect behavior. For them, support for acquiring such skills is important, but it is risky to learn soothing motions with real neonates. Additionally, many caregivers feel uncomfortable attaching sensors to neonates. So, the purpose of this study is to effectively support learning and training expert soothing motion with less invasive methods. Then we propose smartphone-based teaching system for neonate soothing motions. The system uses a smartphone and a stuffed toy for easy training at home without special equipment. First, users put a smartphone into a waist pouch and attach it to a stuffed toy. Then they train soothing motion with it as if it were a neonate. A smartphone assesses the posture angles of a stuffed toy and the magnitude of acceleration when soothing it. According to user's action, this system provides a real-time feedback on the screen and through audio. This is a video showing how to use the application and its screen at that time. Users adjust their movements while looking at the screen and listening to audio. As dated works about neonatal nursing support systems, some utilize wearable sensors on a baby to monitor physiological data and the shaking of the baby to detect danger. Others proposed mobile sensing platforms that can provide unobtrusive and continuous measurements of physical contact in naturalistic home interactions. While these systems aid child care by measuring the actual condition of neonates, research for first-time caregivers has also been conducted on training systems. Per baby, a baby-type simulator with multiple sensors assists in learning soothing motions. Using sensors embedded in the simulator, users' actions are evaluated in real time and feedback is provided through the simulator's movements and the application. This method is non-invasive, but per baby requires specialized equipment, making it difficult for users to casually practice at home. Our system is for first-time caregivers and we focused on cradle hold during the neonatal period. This is the basic posture to hold neonates before his or her neck control is established. And we consider midwives experts in neonatal nursing, so we aim to create a system to learn their motions. First, we determine the true values for the posture angles and the magnitude of acceleration when soothing a neonate. We asked the midwife to perform soothing a baby doll with cradle hold, and data was collected for 1 minute. The posture angles comprise adduction angle and the inclination angle. As a figure, we defined the adduction angle as the rotation angle around the axis of doll's body towards a midwife from a horizontal position, and the inclination angle as the doll's head rotation angle upwards around its chest from horizontal position. The table shows each average values. This system is implemented using a far-away P30 Lite smartphone. Smart home built-in sensors capture the posture angles and the magnitude of acceleration. We focused on two types of data that can be obtained through a smartphone among the types of information collected by per baby. Next, feedback is provided on screen and through audio. The smartphone screen displays a 3D model of a neonate that synchronizes with the motion of the smartphone and the text indicating the posture angles and warning, and alerts that indicate the direction to return to appropriate posture angle. Through audio, a baby's crying sound indicates that the sensor value deviates from the threshold value. We assessed the system's effectiveness through a user study involving two groups, that is Group V and Group V plus PS, which had different methods of learning the soothing motions. First, the participants really performed soothing motions with cradle hold for 1 minute, using a baby doll equipped with an X-Sense sensor. In the learning phase, Group V watched the video about soothing by a midwife and used a stuffed toy alone. Group V plus PS not only watched the video, but also used the system with the stuffed toy. Finally, they performed soothing motions with cradle hold using the doll for 1 minute again. As a result, in the case of inclination angle, a significant difference was observed. In other words, the position of the doll's head was higher in the Group V plus PS. For neonates who could not lift their heads, the neck angle is directly linked to the ease of breathing. This system is effective in teaching the inclination angle, so this result demonstrates useful for ensuring the safety of neonates. In terms of adduction angle, both groups showed no significant difference. However, as the post-training data, Group V plus PS had a smaller standard deviation than Group V. The video alone might have made it challenging to grasp the correct angle, leading to varied interpretations in Group V. And regarding acceleration, there is no significant difference, but Group V plus PS deviated further from the true value. The system has more feedback elements on posture angles than acceleration, so it reinforced their intention to imitate the correct posture angles. As a result, they may have performed less intense shaking. As limitations of this study, angle offset occurs when improperly attaching the phone to the stuffed toy or when the system does not start with the phone in the horizontal position. In such cases, the true value of the angle cannot be told accurately. In addition, smartphone-based approach has limited information that can be measured or provided. In this implementation, for example, it cannot measure where the user touches and holds the stuffed toy. Next, in this study, we defined the true values based on data from a single midwife. Therefore, the credibility of the true values as representative of the appropriate motions may be limited. However, given the focus on assisting learning of expert movements, we consider the system effective since it helped the participant motions approach midwife's motions. Moreover, variation in neonatal behavior and preferences may alter the most effective soothing motions. Thus, true values and thresholds should be further refined through collaboration with midwives and experts in psychology. Finally, to further explore the effectiveness of the system, it would be valuable to assess effectiveness for long-term training or with different types of soft toy. At last, this is summary. That's it.